Right now, somewhere on Earth, a machine the height of a 40-story building is standing on a pad, filled with enough explosive energy to level a city block on purpose. In the next 8 minutes, it will accelerate from 0 to over 27,000 kilometers per hour, shed most of its own body weight, survive temperatures hot enough to melt steel, and deliver a payload into a vacuum 400 kilometers above your head. This is how a rocket launch actually works, step by step, second by second. Let's break it down. Every launch begins long before the engines ignite. Hours earlier, cryogenic propellants, usually liquid oxygen at around -183 degrees Celsius, and either liquid hydrogen, kerosene, RP1, or methane, are loaded into the rocket's tanks. As these supercooled liquids boil off inside the tanks, you'll see that iconic white fog venting from the vehicle. That's not smoke, that's frozen air condensing on the freezing cold metal skin. At T-10 seconds, the launch computer takes over. No human reflexes are fast enough for what's about to happen. Ignition sequence start. Here's something most people don't realize. The engines don't fire all at once, like a light switch. They ignite in a staggered sequence, often outer engines first, then inner ones, so the launch computer can verify each engine is producing healthy, stable thrust before committing to liftoff. If a sensor detects an anomaly, a pressure spike, an uneven flame pattern, the whole sequence aborts. Hold down clamps, stay locked, and the rocket sits down safely. This is called an RSLS abort, and it's happened on real missions, including space shuttle launches, mere seconds before liftoff. Assuming everything checks out, the onboard computer confirms full thrust. For a vehicle like SpaceX's Falcon 9, that's around 7,600 kilonewtons from 9 Merlin engines combined, more than enough to overcome the rocket's own weight. The hold-down clamps release, liftoff. The first few seconds are the slowest and the most dangerous. The rocket is at its heaviest, moving at its slowest speed, which means it has the least aerodynamic control. Engineers call this the period of maximum vulnerability to wind shear. Guidance systems constantly adjust the engine nozzles, a process called gimbaling, tilting them by fractions of a degree to keep the vehicle balanced on a plume of fire. As the rocket climbs, it begins a maneuver called the pitch-over, or gravity turn. Instead of flying straight up the entire way, it gradually tilts onto its side relative to the horizon. This isn't optional, it's essential physics. Flying straight up would mean fighting gravity the entire ascent. By curving the trajectory, the rocket uses gravity with it, gradually converting vertical speed into the horizontal speed needed to achieve orbit. Remember, reaching space is easy. Staying in orbit means going sideways fast, roughly 7.8 kilometers per second for low Earth orbit. About a minute in, the rocket punches through max Q, the point of maximum aerodynamic pressure. This is where the combination of speed and thinning atmosphere creates the greatest structural stress on the airframe. Engineers sometimes throttle the engines down slightly here to reduce strain, then throttle back up once past it. You'll often hear, "Vehicle is go at max Q" in mission commentary. That's the call-out confirming the rocket survived its most physically stressful moment. By now, the sky outside the rocket would already be turning black. The vehicle is climbing through the stratosphere, engines still roaring, first stage doing the heavy lifting. A rocket carries almost all of its mass as fuel. That means the single biggest design problem in spaceflight is this. As you burn fuel, you're hauling around empty, useless tanks. The solution, first proposed in the early 20th century by pioneers like Konstantin Tsiolkovsky, is staging. Build the rocket in sections, burn one section's fuel, then throw the entire section away, so the rest of the rocket doesn't have to keep accelerating dead weight. Around 2.5 minutes into flight, the first stage has done its job. It's used the bulk of its propellant to get the vehicle up to roughly 2 to 2.5 kilometers per second and beyond the thickest part of the atmosphere. The onboard computer commands main engine cutoff, MEO. The engines shut down almost instantly. For a moment, everything goes quiet and the vehicle coasts, weightless. Then explosive bolts or pneumatic pushers fire, physically separating the spent first stage from the rest of the rocket. Small separation thrusters, sometimes just cold gas jets, push the two halves apart to make sure they don't collide as the second stage's engine ignites right behind it. This is one of the most visually dramatic moments of any launch. You'll often see it captured on camera as a bright ring of fire, sometimes nicknamed the Ring of Fire shot, as the second stage engine ignites just as the spent booster tumbles away below. For expendable rockets, that first stage is now debris, falling back toward the ocean or a designated drop zone. But for reusable vehicles like SpaceX's Falcon 9, this is where the booster's second life begins. It executes a boost-back burn to reverse its trajectory, uses grid fins to steer itself through the atmosphere, and performs a final landing burn to touch down, either on a floating drone ship or back at the launch site. It's a controlled fall from space, arguably as complex as the ascent itself. Meanwhile, up top, the mission continues. The rocket is now far lighter, flying on a single upper stage engine optimized for the near vacuum of high altitude. These engines typically have larger, wider nozzle bells than first stage engines, designed specifically for efficiency where there's little to no atmospheric pressure pushing back against the exhaust. This is the phase most people never see, because by now the rocket is far too high and too fast for any ground camera to track it. Everything is happening on telemetry, on data, engineers in mission control watching numbers climb on a screen. The second stage's job is deceptively simple to describe and brutally hard to execute. Take the vehicle from a suborbital trajectory, one that would eventually curve back down and hit the Earth, and convert it into a stable orbital trajectory, one that continuously falls around the planet instead of into it. Think of it this way, an orbit is really just falling with enough sideways speed that the ground curves away beneath you exactly as fast as you fall toward it. To achieve that for low Earth orbit, the vehicle needs to reach roughly 7.8 kilometers per second, about 28,000 kilometers per hour, while also being at the correct altitude and pointed in the correct direction. Get any one of those three variables wrong, and you either fall back to Earth or fly off into an unwanted, useless orbit. The second stage engine doesn't just burn for a fixed amount of time. It's constantly guided by an onboard computer running real-time trajectory calculations, adjusting thrust angle and duration to hit a precise target, a specific altitude, velocity, and inclination. This burn can last anywhere from 5 to 7 minutes depending on the mission and the target orbit. Once the required velocity and orbital parameters are achieved, the engine shuts down, second engine cutoff, or SECO. At this exact moment, the vehicle and everything attached to it officially becomes an orbiting object. It is no longer flying, it is falling around the Earth, forever, or at least until atmospheric drag or a deliberate maneuver eventually brings it down. For missions headed further out, to geostationary orbit, the Moon, or beyond, this may not be the final burn. Some second stages coast for extended periods, sometimes hours, before reigniting for a second burn to raise or reshape the orbit, timed precisely to when the vehicle reaches the right point in its path. Let's back up slightly, because fairing separation actually happens earlier in the flight than most people expect, usually around 3 to 4 minutes after liftoff, while the second stage is still burning. The payload fairing is the rocket's nose cone, a protective clamshell shroud that shields the satellite, spacecraft, or cargo from aerodynamic pressure, heat, and acoustic vibration during the thickest, most violent part of the ascent through the atmosphere. Once the rocket climbs high enough, typically above 100 to 120 kilometers, where the atmosphere is thin enough that aerodynamic heating and pressure are no longer a threat, that fairing becomes dead weight. Keeping it attached any longer would just waste fuel hauling useless mass toward orbit. So, using pneumatic pushers or small pyrotechnic charges, the two fairing halves split cleanly down a seam and drift away into space. This moment often produces one of the most beautiful shots of the entire mission, the fairing halves tumbling slowly against the blackness of space, sometimes with the Earth's curve glowing in the background, sometimes catching sunlight in a way that looks almost unreal. With the fairing gone, the payload, whether it's a communications satellite, a crewed capsule, a space telescope, or a batch of internet satellites, is now exposed at the very top of the stack, riding along as the second stage continues its climb and burn toward orbit. Once the second stage completes its orbital insertion burn and reaches the target orbit, the final act begins, payload deployment. Springs, pushers, or clamp band release mechanisms gently separate the payload from the spent rocket stage, often with a relative velocity of just a fraction of a meter per second, a gentle nudge rather than a violent kick to avoid damaging delicate hardware like solar panels or antennas. From here, the satellite is on its own. Solar panels unfold, communication systems power up, onboard thrusters may fire to fine-tune its position, and the rocket's job, from ignition to this final release, is complete. So to recap, liftoff and the gravity turn get the vehicle off the pad and curving toward orbit. First stage separation sheds dead weight the moment the booster has done its job. The second stage's orbital insertion burn does the real work of achieving orbital velocity. And fairing separation, followed by payload deployment, delivers the actual cargo, the reason the entire mission exists, into space. Every launch is really just this same sequence, repeated with different rockets, different payloads, and different destinations, from resupplying the International Space Station to sending rovers to Mars. If you found this breakdown helpful, subscribe for more deep dives into how spaceflight actually works, and let me know in the comments which stage of the launch you want us to cover in more detail next.